Hello, everyone, and welcome to today's webinar hosted by SPIROL, where we will talk about coiled spring pins and specifically their unique benefits when used in dynamic assemblies. This will be an interactive webinar where you can submit your questions during the presentation, and we will answer them after the presentation has concluded in the Q&A segment of the webinar. You can submit your questions at any time by clicking on the Q&A button at the top of the screen. This webinar is being recorded, and we will make the recording available in the resources section on SPIROL.com as well as on our YouTube page. And with that, I am pleased to introduce today's presenters, Mike Pascoe and Adolf Valashek. Mike and Adolf are two of SPIROL's strong team of application engineers with a collective 22 years of experience at SPIROL between them. These two are definitely a great resource for all things related to pinning, and they are ready to help you with your next design projects. Take it away, Mike and Adolf.
Thanks, Christy. I'm Mike Pascoe, SPIROL's group lead in applications engineering. I've been with the company over 20 years and enjoy supporting our customers with product recommendations and design assistance. Our objective is always to partner with customers as early as possible to ensure products purchased are best for the application with both installation and cost properly considered. Given the diversity of our customer base, we see applications from a wide variety of industries, and every new application provides SPIROL and our customers opportunity to learn from one another. It's this engagement we find most rewarding from a design perspective. And thank you all for attending.
Thanks for our introduction, Mike and Christy. My name is Adolf. I have a master's degree in mechanical engineering, and my background is full of machine tool design, product development, and academic research. As an applications engineer in SPIROL, I thoroughly enjoy the variety of customer applications and the challenges that I get to help resolve, as well as the exposure to just so many different industries. So, as the webinar's name suggests, we'll talk all about dynamic applications. And for that, we'll need to go over some of the applicable definitions and terms used when talking about dynamic loads, fatigue strength, as well as how fatigue life is actually estimated, with some background theory. We'll review some examples of applications that we have encountered over the years that are dynamically loaded and talk about which fastener is best suited for these applications while comparing their features and performance. We'll also go a bit more in depth into materials that are used to make the pins and how they affect the endurance of the application, as well as some more general guidelines for maximizing the service life of your application. But first, I would like to introduce our company and explain what we do for those who are not completely familiar with us. SPIROL is a global manufacturer and supplier of engineered components that are used for fastening, joining, and assembly. We have 12 major product lines, and each one is designed to improve product quality, simplify the assembly process, and/or to reduce the overall cost of the assembly. We are the only company who designs and manufactures both our engineered fasteners as well as the installation equipment for our fasteners. Our focus, though, is not just about supplying the high-quality product, but it's in working with our customers as early as possible in their design stage to help them choose not only the fastener, but also provide the critical recommendations between our product and their components so that when the assembly goes together, it stays together for the intended life of the assembly. To truly understand SPIROL, let's go back in time and relive the story behind the founding of our company. Hermann Kohl, a German scientist and engineer, emigrated from Germany to the United States in the late 1940s. After his arrival, he worked for the US Air Force, where he was trying to solve a peculiar problem with fastening the turbine blades to the rotor on early jet engines. The Air Force tried to use bolts and nuts, double pins, and a traditional slotted spring pin, but nothing worked as the fasteners kept either failing or falling out of the assembly. This was primarily due to the vibrations within the assembly, which caused the nuts and bolts to vibrate apart and fatigued the pins or enlarged the hole, resulting in the pin falling out of the hole. In a spark of brilliance, Mr. Kohl tried to take the spring pin concept of the slotted pin and take it a step further to provide more flexibility through coiling a thinner strip. The coiled spring pin's superior flexibility and shock and vibration absorbing properties preserved the integrity of the hull and held the engine assembly intact for the intended life. After his time in the Air Force, Mr. Cole took the coiled pin to the market, and the rest is history. So let's first review the terms and concepts of dynamic applications. We're going to get a little bit technical, so I really want to take a minute to explain these terms and make sure that everyone understands them. So what exactly is a dynamic load? Well, simply put, it is any load that changes over time. This can be either a pulsating force, imagine pushing and pulling onto something repeatedly. It can be a random vibration, like a car driving on a rough road, or it can be a shock or an impact. Imagine a hammer hitting something. So when we're talking about dynamic loads, we want to have a complete picture about what is going on. After determining the type of the load, it can be further described by these parameters. Mean stress component, which is the average or middle value of the curve. Amplitude is the amount by how much it oscillates over time, or the peaks and the valleys in the graph. And frequency, which is essentially how fast the load changes over time. And when talking about shocks or impacts, these are best described by how much energy they carry, which would be represented by the area under the curve, and their spectrum. Imagine comparing a hammer hitting an anvil versus a foam stick hitting a mattress. Both of these are impacts, but they have vastly different consequences.
SPIROL addresses dynamic loading in a wide variety of applications. Generally, any powertrain application, regardless the industry, presents the need for products capable of performing under dynamic loading. Engines, transmissions, gears, axles, differentials, all subject installed pins to some form of reciprocating force or load. Mining equipment is one example of an industry where pin joints are often subject to very high shear, impact, and vibration. Power generation is similar to powertrain applications, though machines designed for this industry are typically orders of magnitude larger. And due to the scale of these assemblies, SPIROL's wide variety of pins, up to 20 millimeters or 3/4 inch in diameter, are an important capability. Machine tools and other industrial equipment prevent a broad spectrum of dynamic applications, wherein dynamic loading can be highly variable, consisting of vibration, reciprocating loads, shocks, or impacts.
So knowing that our application is dynamic and having an idea about the forces that it endures, how do we actually estimate or predict the life of the assembly until fatigue occurs? Well, engineers have a tool for this. It's called the SN curve or Wooler curve, as seen here on the slide. And the curve puts the dynamic stress of the application, which is on the y-axis, in a relationship to the number of cycles to failure, which is on the x-axis here. Essentially, you can either take the stress in the application and find out just how many cycles it is going to last, or take your desired number of cycles and determine the maximum dynamic stress that would be permissible for that life. And as you can see on the chart, the curve typically has 3 sections: low cycle fatigue, time fatigue, and infinite life. Low cycle fatigue is considered to be less than 1,000 cycles. And at that point, the stress or fatigue strength is actually very close to its static strength. And with more and more cycles, the strength under fatigue drops. This is the timed portion of the curve, where we see the life change a lot depending on the stress. However, once we reach 1 million or 10 million or cycles or so, the drop in strength drops, and we have reached what's called the endurance limit, where the life of the application is considered infinite. Some metals don't have this property, though, and continue to drop in strength even past 1 million cycles. But it is universally agreed that approximately 100 million cycles is more than enough cycles for any application to be considered infinite, and that's what we call the endurance limit with those. So now that we know how a life of an application can be estimated, where or how do we get the SN curve of a particular part? Well, to fully define the SN curve for something, we only really need the endurance limit. On the previous slide, we learned that the low cycle strength is not much different from the material's yield strength, and that it kind of drops to the endurance limit after 1 million or so cycles. So the endurance limit is always a portion of the yield strength, and it is specific to material application and load cycle combination. And for example, it's different for all grades of steel. It's different for the application type. It's different for the type of stress created by the load, be it shear, bending, torsion, tension, or combinations thereof. The amplitude ratio of the pulsating force makes a difference. The size of the part also affects the endurance. Surface quality and presence of any notches is another factor to consider, as well as any corrosion that might be weakening the part over time. So how do we actually calculate the endurance limit? In simple textbook cases, it can be calculated from the material's yield strength and evaluating and applying all factors that we've mentioned on the previous slide. But the more complex loads, stresses, and scenarios, the more lengthy and kind of indeterminate this calculation becomes. Therefore, it's often simpler to set up a fatigue test jig and determine the endurance limit empirically, which would be directly applicable, which is exactly what we did for cold pins. But more on that a little bit later. Let's now take a look at some real-world applications that we have worked on with our customers.
Spiral coiled spring pins are often used to retain gudgeon or wrist pins in pneumatic compressor pistons. Here, the coil pin's ability to self-retain and withstand high vibration and cyclical loading are critical. The coiled spring pin eases hole preparation, installation, and also improves service life. Another great example is a bucket tooth pin for excavators. Imagine how tough pins must be to withstand loads in the variety of environments where this equipment is used. Here, the coiled pin allows bucket teeth to be pinned rather than welded, which greatly reduces difficulty associated with their replacement. Also, in heavy construction, though smaller scale, would be the gear and shaft assembly driving a dump truck tarp mechanism. A cross-section is provided of a very typical shaft and collar application here, driving a golf caddy. It's worth noting that pin chamfers extend beyond the collar, and this is an excellent strategy for ensuring complete engagement where there is clearance available for the ends of the pin. Another application where coiled spring pins' dynamic capabilities are realized would be as anti-splay pins in automotive and heavy equipment leaf springs. Here, the coiled spring pins are used to prevent rotation of the individual leaves relative to one another. And given the loads occurring during cornering, impacts due to variation in road surface, high vibration, this really is a textbook dynamic application. So with these applications in mind, let's cover the various types of pins that could potentially be used and focus on their unique characteristics. We'll start with solid pins. This product's great pitfall is its inability to absorb shock as it is a solid object. In addition, host holes must often be reamed and precision matched, as a very slight change in interference or fit will have a tremendous impact on installation force and potentially performance. It's always recommended solid pins be harder than the host material, and under reciprocating load, reversal of forces can incrementally displace the softer host material, eventually elongating the holes. As a result, shock from force reversal will be amplified, leading to ever-increasing deformation. Eventually, the pin will fail in fatigue, and the hole will be left permanently damaged. A damaged host hole would require rework and potentially replacement of the entire component. The next available option is the slotted spring pin. As this solution is a functional spring, it does absorb shock, though its ability to do so is limited by width of the slot once installed in the hole. Once the slot closes, it functions as an inflexible solid tube with the same consequences associated with the solid pin, meaning potential for permanent hole damage. A benefit in comparison to the solid pin is that spring pins do not require precision machined and matched holes, as due to the pin's flexibility prior to installation, much wider hole tolerances can be accommodated. The slotted pin's pitfall is that its performance largely depends upon orientation of the slot being in line with the load, and it's not always possible to automate slot orientation in high volume production. In addition, stress in a slotted pin is concentrated directly opposite the slot, much like the binding of a book. It is this location where fatigue cracks will appear and further propagate. When slotted pins fail in fatigue, the application must be serviced, though often host parts can be reused. The coiled pin was specifically designed to absorb shock and vibration beyond that which the slotted pin is capable. Its unique 2¼ coil formation allows for greater spring response as compared to the slotted spring pins that can butt. A coiled pin's inner coil can continue moving, allowing for much greater flexibility. As with the slotted pin, holes do not need to be precision machined, but unlike slotted pins, coil pins do not have or possess the same Achilles heel, as stress is much better distributed uniformly through its cross-section. This also means radial pressure exerted on the hole is uniform, which prevents host damage and allows for repeated use. The other benefit of the 2¼ coil formation is that performance is independent of pin orientation. It is also available in 3 duties, light, standard, and heavy, which allows the designer to select the optimal combination of strength and flexibility for their specific application. Should the coil pin crack due to fatigue, which will require more time than competing products, cracking will propagate from the outer coil, typically within the shear plane, slowly work its way inward, and as that crack progresses through the coils, the coil spring pin will continue transferring loads until its cross-sectional area is reduced to the point at which shear occurs. So how do pins compare in numbers? We've performed in-house experiments supervised by renowned academic researchers on a machine which simulates a reciprocating shear force acting on the pin with adjustable load. In a scenario where the dynamic load was 50% of the pin's overall strength, the coiled spring pin lasted approximately 5 times as long as the slotted spring pin on average. Not only that, a clear increase of the overall endurance limit was also observed, which means that for the same force and nominal diameter, a coiled pin can achieve an infinite service life, whereas a slotted pin will fail prematurely. Another factor determining service life of the application is pin material. Coil pins are available in high carbon steel, chrome vanadium alloy steel, and 2 kinds of stainless, austenitic nickel stainless steel and martensitic chrome stainless steel. Some of these materials are heat treated, which improves overall performance and consistency of spring characteristics. Heat treating provides higher shear strength and hardness, resulting in pins that are suitable for use in hardened host components. In terms of operating temperatures, once heat treated, these materials will provide proper performance at temperatures ranging from -45 to 155 Celsius or -50 to 300 degrees Fahrenheit for high carbon steel and alloy, and as high as 260 degrees Celsius or 500 Fahrenheit for the martensitic stainless steel. Austenitic stainless steel cannot be heat treated, and it work hardens as it's cycled. As a result, this material does not absorb shock well, and it's not recommended for use in applications where dynamic loading is present. Austenitic or 300 series stainless steel has lower shear strength and hardness as compared to the carbon and alloy steel, as well as the 420 chrome. In addition, this material is generally not suitable for use in hardened components. As high temperatures do not significantly affect this material's mechanical properties, it can be used in a wider range of temperatures than our hardened materials. And the effective range for this material is -185 Celsius to 400 Celsius, or -300 Fahrenheit to 750 degrees Fahrenheit. The main difference between these materials is in their comparative endurance. As we mentioned earlier, we developed a general relative SN diagram for coil pins. We've spent hundreds of hours rigorously testing the pins to record single data points at 1 million cycles plus. The provided diagram is generally acceptable or applicable to all pin sizes, and the principles carry over to other duties as well. We can see that with high carbon steel, infinite life is achieved at loads below 12% of the total rated shear strength of the pin. Austenetic's performance is worse at only about 8.5% of its total shear strength. And keep in mind its shear strength is lower to begin with. Martensitic stainless steel outperforms even high carbon steel and can reach infinite life at as much as 16% of its total shear strength. These are general numbers for a very general scenario, and as we've discussed, even slight changes to operating conditions will yield different results. Nevertheless, they remain a good starting point when selecting pins for use in dynamic applications. We would recommend sizing pins such that load not exceed 10% of their rated shear strength in most dynamic applications where infinite life of the assembly is desired.
So all that we have talked about today was in reference to achieving the ultimate goal, to maximize life of an assembly. We've already established that coil pins are superior for dynamic applications. Well, what else can we do? Let's put that into some more concrete design guidelines. Generally, we should always get a more durable material and minimize stress. But how do we do that? A couple slides back, Mike was talking about the SN diagram that we have developed for the different materials of coil pins, where you could see a higher endurance limit of the 420 martensitic stainless steel. This is the favorable material for dynamic applications, even in environments where corrosion resistance is not of an explicit concern. Where there is a general atmospheric corrosion, the added benefit of corrosion resistance will prevent the surface from corroding and creating local stress razors, which would compromise the service life. And the increase in service life by switching to 420 martensitic will be dramatic. Martensitic stainless steel is not the solution for all applications, though. In extremely corrosive or high temperature environments, the better corrosion and temperature resistance of austenitic stainless steel would actually make it function slightly better. And in the most special of cases, we can also look into using 316 stainless steel for its even superior corrosion resistance, or even Inconel for some of the ultra high temperatures or sour gas environments. Changing the material of the pin is usually the simplest change that can be made. After that, it's all about minimizing the stress. Without going into more severe design changes, it's worth to investigate the forces that act on the pin and if they could be optimized. Obviously, if we could just lower the force that acts on the pin, that would be the best, but that's usually non-negotiable. What could be done, however, is changing the dynamic load mode by isolating the assembly from harsh vibrations and preloading the assembly. The principle of preload is widely used in dynamic applications. The coefficient that determines the endurance limit is most favorable with a pulsating force, which is the one up here, as opposed to an alternating force. The load curve also plays a role. A sine curve is the most gentle on the application, whereas, for example, a rectangular pattern is essentially a series of repeating shocks and impacts. After that, we can take a look at increasing the amount of pin material. More material means a larger cross-sectional area of the pin and therefore less stress. We can either increase the pin diameter itself while still staying within the geometrical constraints of the application, which, for example, in a shaft and hop assembly, the pin diameter should not exceed a third of the shaft diameter. Another option is to move to a heavier duty pin. Before making the move to a heavy duty pin, though, we need to make sure that the host material is sufficiently hard and strong to accommodate it. If we used heavy duty in aluminum, for example, the comparatively high stiffness of the pin would have essentially the same consequences as a solid pin, and the service life could actually be decreased. Generally speaking, it's better to go to a larger diameter standard duty pin before moving to a heavy duty pin, except in very specific applications. Another great improvement can be made by minimizing the movement of the on-force reversals. To accomplish this, hole sizes between mating components should be matched so that no part would have an excessive clearance that would result in shocks during force reversals. Ideally, the holes would be drilled as an assembly to have a uniform diameter, but a maximum difference of 0.05 millimeters or 0.02 of an inch should be targeted if that is not possible. Last but certainly not least, you should always minimize shear plane separation to achieve a clean shear load. The shear planes should be a maximum of 0.13 millimeters or 0.005 of an inch apart from each other, which is represented by clearance in the hub and shaft assembly, for example. And the more clearance and the bigger distance, that introduces an additional bending stress. To elaborate, if shear planes are separated by 2 millimeters, a 4 millimeter heavy duty coil pin would see an increase of combined stress of 28%. Now, you may think that there is, if someone is going to have a 2 millimeter clearance between their hub and shaft, that's not possible, and you would be right. But if there is a 1 millimeter countersink on each side of the hole, that creates essentially the same effect. Countersinks should be removed from wherever shear occurs.
This may have been a lot to ingest in one sitting, so let's summarize the key takeaways here. First, we've demonstrated that coiled spring pins are the superior fastener for dynamically loaded applications. So whenever you identify that an application will have a changing force over time, consider using a coiled spring pin. In regard to pin material, 420 martensitic chrome stainless steel will provide the highest endurance limit as compared to our other standard materials. This includes high carbon steel, even when comparisons are made in oil-rich environments where corrosion is not of concern. To maximize service life of the assembly, minimize stress on the pin by selecting the most suitable diameter and duty, as well as eliminating any unnecessary countersinks or other design features that separate the shear planes and introduce bending.
And to put that into a practice, I have a great example that will illustrate just how the different types of pins react in dynamic applications. A manufacturer of agricultural equipment attachments contacted SPIROL because they were experiencing fatigue failures with their current slotted spring pin in a hay rake assembly. The pin is used to retain this hub into this shaft here. What I love about this application particularly is that the solution is totally contrary to what you might think would be the solution when it comes to pinning. They contacted SPIROL because they had read that coil pins had better service life, especially in dynamic applications, and declined SPIROL's complimentary application engineering assistance, and just simply requested samples of a heavy-duty coiled spring pin, the same size that they were using with the slotted spring pin. A few weeks later, they contacted SPIROL yet again, this time to actually request the application engineering assistance. They said that the heavy-duty coiled spring pin also failed in the application, so that they also tried a heat-treated solid pin, thinking that they needed an even stronger pin for the assembly, and that failed too. So upon reviewing the application, SPIROL Engineering quickly learned that the host material in which the pin was used was non-heat-treated cold-rolled steel. The failed assemblies were evaluated, because they were graciously provided by the customer to us, and to determine the root cause of the failures. And in each instance, we found that the hole in which the pin was used was elongated. All of the pins that failed in the hay rake assembly, the slotted spring pin, the heavy-duty cold spring pin, and the heat-treated solid pin, were actually too stiff for the soft material. The result was that as force was applied on the pin, none of these pins were flexible enough to absorb the shock and vibration, and the pin simply transmitted the force onto the whole wall, and that resulted in deformation. And once the hole was elongated, any force on the pin was exacerbated now due to the movement of the pin within the widened hole on force reversals. This was further compounded by a large countersink on the entrance to the hole, which introduced an additional bending stress on the pin. To solve the problem, rather than going to a stronger pin, the hay rake manufacturer actually needed a more flexible pin. They needed a pin that was strong enough to resist the dynamic forces that occurred during use, but one that was also flexible enough to absorb the shock and vibration to isolate the hole from the force versus simply transmit the forces onto the whole wall. The countersink also needed to be removed. It was also discovered that the other spring pins were corroding, even though that they were zinc plated. What the hay rake manufacturer didn't realize was that zinc plate is primarily recommended for slotted pins and coil pins only to resist galvanic corrosion where that is of concern, not for atmospheric corrosion protection. This is because for any product that has a hole in it, only the outer diameter and surface gets full coverage of the zinc plate. The inner diameter only gets about 1 diameter's worth of plating, which is called throw. Because of this, the spring pins were essentially rusting from the inside out. So therefore, in addition to changing to a standard duty cold pin versus a heavy duty slotted or cold pin, SPIROL recommended that the hay rake manufacturer changes from a zinc plated high carbon steel pin to a plain 420 martensitic stainless steel. The 420 stainless provides great corrosion resistance in this application without any need for subsequent coating or plating. And as we have established, 420 stainless has superb fatigue resistance in dynamic applications. So if you'd like to read more application stories like this one, study some of our in-depth technical white papers, or learn more about pins in general, I encourage you to visit SPIROL.com and wander through our resources section.
We also have 3D models of our products available from our website that you can download or insert directly into the model of your assembly.
If you're working on a new design, involve SPIROL as early as possible. We will conduct a comprehensive evaluation of your application and then provide you with a detailed engineering report, complete with samples for testing and approval.
All right, thank you, Mike and Adolf. Now let's move into the question and answer segment of the webinar. We've had some great questions come through already. If anyone still has a question, you can continue to submit them by using the Q&A button at the top of the screen. Okay, the first question: what are the benefits of using 420 stainless steel coiled spring pins versus a plated carbon steel coiled pin?
There are quite a few, Christy. So 420 martensitic is, number one, very corrosion resistant. It's excellent in use with mild alkalins or acids, detergents, things of that nature. And that protection is lifelong. So as long as there is free oxygen present in the environment, any damage to its protective oxide layer will spontaneously heal itself. That's a significant departure from coatings and platings that are, generally speaking, sacrificial. So they have a finite lifespan. And even when they provide fantastic performance initially, eventually they will drop off the proverbial cliff. Once that material has been consumed, you are done. And now the part is subject to both galvanic attack and general corrosion. We have discussed at length the benefits of 420 in regard to fatigue life. There is no doubt, based on the evidence that we've amassed, that there is a significant benefit there for any articulating assembly that's going to subject the pin to cyclic loading, especially any shock and impact. I think also worthy of noting is that in industry today, we have ever increasing cleanliness requirements, and the 420 chrome, unlike high carbon steel and alloy steels, is not oil quenched as part of the heat treating process. This is performed in a vacuum furnace. So we have a very good control over product manufacture, as well as the secondary wash process, and we don't introduce any potential for further contamination during the heat treating process. As a result of the standard materials available that possess that kind of strength and endurance, 420 martensitic stainless steel will definitely be the best choice.
Okay, thank you. Okay, another question. The coil pin started in aerospace. Are there modern aerospace applications?
Of course, one of the applications that we see coming back and forth is, for example, in a life vest, where the pin is used as a hinge pin to pull the trigger and inflate the vest. But of course, we also have more critical applications where the pins are used in brake assemblies, which is a very critical application for aerospace, as well as many other mechanical parts of the airplane.
Okay. Another question. I use two slotted pins, one inside the other. Can I replace with a coiled pin?
That's actually an excellent question. So a slotted pin within a slotted pin is unique to the ISO version of that part. ISO slotted pins, if used properly, with the seam or the gaps oriented at 180 degrees opposite one another and properly matched within the correct holes, will provide you with a composite of both pins' shear strength. That is something that if you actually need that shear strength, it's great. But in our experience, many applications where the composite slotted pins are utilized actually don't require that degree of shear strength. And if true, SPIROL's heavy-duty coil pins are often an excellent drop-in replacement for the slotted pins. A really significant benefit of the coiled spring pin is the lack of difficulty comparatively with their installation. So anybody that's tried to do this, number one, if you try to install the pins pre-assembled, your insertion forces are dramatically higher, and that presents some significant challenges in and of itself. If you do install the pins separately, one and then the other internally, unless you are automating that assembly based on the gap, you now have a potential failure mode due to personnel potentially putting that pin in incorrectly. So again, if you actually need the strength of the ISO pins as a pairing in that application, it's not always a bad solution, but many times we have experienced the fact that the shear strength is actually not required, and the heavy-duty coil spring pin provides more than adequate strength.
Yeah, and Mike, also, you remember when we had this application from a customer where the composite pin actually caused the host component to break?
Yes, yes, and that's an important fact. Long term, any application or assembly, there's going to be a failure mode. And if it's a fairly expensive assembly, you generally don't want that to be the assembly itself. So again, pick your failure mode. And if you don't want it to be the larger assembly, you need to have something that's going to shear at some point. And the composite slotted pins aren't always the best solution in that situation.
Okay, next question. How could I calculate the forces needed to press any of these pins in a hole?
This is a question that we get quite often recently, and it is kind of attached to the nature of the coil pin. So what you would be essentially looking for is the stiffness of the pin when it's coiling. When calculating insertion forces of solid pins, of solid pins or dowels, that is a fairly simple calculation where we calculate the displacement of the hole and the displacement of the pin and kind of what pressures will be present. With a slotted pin, that becomes a little bit more challenging because the pin actually springs and is effectively a C-shaped beam. And although there is a analytical equation that you could use to calculate the contact pressure and with the friction coefficients, subsequently the insertion force, it's always better to try and install the pin and measure the forces with some statistics behind it to find the statistical derivation. And for coil pins, we don't even have an analytical equation that could be used to calculate this because the coil pin is just a very complicated geometry, and the beam calculation of the spiral is, I'm not saying impossible to derive, but definitely extremely challenging. And so for controlling insertion force, it's always best to actually measure the insertion forces in your concrete application because hole conditions, hole sizes, the host materials, all of those factors will make a difference. And then you also need to factor in the again, what kind of mean statistical derivation or what is it? The spread essentially of the insertion forces that you will see. So all of that needs to be taken in mind when sizing the installation equipment for the application.
And I think another good point to add to that is the fact that the coiled spring pins, again, they're available in 3 different duties. In fact, 4, we have another even lighter one for very fragile materials and extra light. So the typical ones you'd see in our catalog are light, standard, and heavy. And then at the extreme end of flexibility, we even have the extra light. So rather than tabulating a specific insertion force, we like to actually move down through that sequence of pins where the strength requirements allow and provide you with the optimal combination of strength and flexibility. It's never a good idea to throw more pin in a hole than you need. In terms of automating pins, which is more often than not the driving force behind that question being asked, we always suggest that you implement robust safety factor in terms of sizing cylinders, etc. So for example, if average insertion force were 1,000 pounds, you'd want a cylinder capable of no less than 2,000 to 3,000 pounds, depending upon your materials.
Okay, another question. Are there any particular guidelines for the hole sizing or assembly process to avoid pin flaring during or after assembly?
So in our catalog, we have the recommended holes in which the pin is to be installed. And as we have talked about today, ideally you would want to have any holes or any, if the pin is passing through multiple components, all of these holes should be ideally precision matched, or in the most ideal case, drilled together as an assembly so that they have one uniform diameter with no steps and excellent centerline positioning. If that is not entirely possible, we suggest a maximum deviation of about 0.05 millimeters or 0.02 of an inch, so that the pin wouldn't be kind of flaring out into the other hole when it's installed. And also when talking about dynamic applications, we want to prevent the pin from walking. So if the holes were mismatched, you would introduce an additional potential for this kind of failure mode to occur. So we also, when taking a look into that, we need to have this consideration in mind.
Yeah, I think that covers it well, Adolf. One thing I would elaborate on a bit. Adolf had brought up the issue of walking, and it's really critical to remember that whether it be a coiled spring pin or a slotted spring pin of any configuration, they are in fact functional springs. They are by design intended to conform to the holes that you install them in. So for example, if you were to mismatch your holes in a manner that resulted in the first hole, the pin enters being larger than the second hole, and you have two components that are moving relative to one another, that is the mechanism of the creation of the force vector necessary to cause a pin to move. So whenever you're using a pin that's flexible, it's really critical to make sure that loading is symmetrical and that the pin spring characteristics are properly considered when you assign your hole tolerances. And of course, spiral applications can be of assistance with that in any of your more complex assemblies.
Okay, next question, and this is kind of related to your previous answer. How does the coiled pin retain itself in the hole better than a solid pin?
That's actually a bit of a trick question. So generally speaking, the mechanism of retention for a spring pin is simply that the spring pin is designed to be larger than the intended hole. When you drive that pin into the hole, you are sizing the pin down such that it conforms to the hole. That results in spring tension between the pin and the host hole. That eliminates the need generally for really precise holes. The pin is going to self-retain itself due to that friction and stress. Solid pins, if you've done everything right and very properly prepared your holes, can be retained quite well. But again, there's a cost associated with that. So if you're looking for the lowest installed cost solution and you do not need the precision of tenths or hundredths of a millimeter in terms of alignment, etc., then a spring pin is almost always the best bet. And again, if you properly accommodate or account for spring characteristics and you symmetrically load that pin in the assembly, a walking is not going to be a concern.
Okay, can coil pins be used as shear pins?
That is another great question. So coil pins come with a minimum specified shear force. And for classic shear pins, you would want to have an extremely controlled shear point at which the pin would break. And typically that is a solid pin with a machine groove, which has been tested over and over to have that failure mode in control. Coil pins or any spring pins in general, like I said, have a minimum specified shear force, and usually you would be looking into a maximum shear force that would prevent further damage in your assembly. For example, if the pin would be used as a mechanical fuse. So when you are looking into using a coil pin as a shear pin or a fuse, you firstly need to determine what is the minimum force that it still needs to be able to transfer. From that, we should size the actual pin and then only perform tests to make sure that the assembly would be protected from the excessive higher shear forces and make sure that the pin would break somewhere in your desired area.
Yeah, I think that also does a really good job of covering it. And to again expand on that just a bit more, when Adolf talks about a reduced cross-sectional area as your defined break point, typically with a solid pin, that there's a great deal of simplicity there. You make an undercut, you have a cross-sectional area, and you know what your material's yield strength is. With the spring pin, be it slotted or coiled spring pin, there is more variation in your processes. You have a heat treated part with a certain window. So there are simply more variables at play that affect your ability to get a very defined point. So in any event, that's the reason why we always provide a minimum shear strength for the pin, which is critical, but we do not generally sell them as shear pins per se.
Okay, another question. How does temperature affect the performance of pins in special cases of low temperatures?
So in special cases with low temperatures, as you cool down the assembly, it can actually embrittle the material. So I'm sure that you have seen a couple of movies where they, I don't know, critically freeze something, throw it on the ground, and it just shatters into pieces. And that is maybe not as extremely, but to the same effect that would also happen with pins. So if you had applications with close to an absolute zero temperatures, the pins would become a bit brittle.
Okay, this question is a little longer. We use coiled pins and friction hinges. We had to do a lot of testing to calculate exact hole diameters to obtain desired torque. Are there any charts allowing us to calculate torque versus hole diameter?
The answer to that would be no. If you're looking to achieve very specific swing torque in an assembly, beyond the general parameter, like let's say, for example, with a cosmetic case, we manufacture coiled spring pins specifically for that industry. And the general requirement is that that lid, once open, maintain its position relative to the base. That's just for the person that's utilizing it to have access to the product. That is the kind of friction that we are targeting. Very specific values generally require much more costly and elaborate solutions. So you're talking about hinge mechanisms that are effectively clutches. So in any event, no, there is no chart for that. What we do try to do is through an iterative process of evaluation, if the material is strong enough to withstand it, we can move through the duties of coiled spring pins and try to find the one that provides you the best balance. And again, with a practical cost point for the product.
Yeah. And to your point, Mike, we've just had a customer who was sizing the hole so that they achieve a certain swing torque in a cosmetic case application, and they required a lot of swing torque for the normal cosmetic pin, and they actually undersized the hole below what our normal recommendation would be, and they ran into installation problems subsequently because the hole diameter was just so small that it was actually smaller even than the chamfer diameter, so the pin had a hard time entering the hole. So we have to keep the different duties in mind, and if a higher friction or higher swing friction torque is desired, we need to move up a duty, for example, if the host material is suitable to accommodate it.
Absolutely. Another very good real world example that comes to mind historically would be, we're all familiar with the laptops that we use every day. Generally speaking, if any of you have ever had the opportunity to pull apart one of these hinge mechanisms, they're quite elaborate and they're quite costly. We had a customer that was working for a nonprofit trying to introduce laptops to economically depressed areas for school children. So for that target audience, that very fine polished movement of the hinge at specific swing torques simply wasn't necessary. They wanted the lid of the part or the screen simply to hold its position. And they were able to, in that particular instance, provide enough aluminum underneath that plastic cover to accommodate a coiled pin. And a coiled pin presented a pretty substantial reduction in overall cost for that hinge.
Okay, so somebody submitted a picture along with a question, so we're going to try to pull that up right now. Can you guys confirm whether or not, can you see it? Okay,
Yep.
Awesome. So the question is, can I use a pin as a pivot axis in one of the parts?
As a pivot axis in one of the parts. Absolutely. This is one of the use cases that we see all the time. To use a coil pin in a situation like this, you are retaining the pin in wherever part you have more material, and it always needs to be at least, if we're talking about the outer parts, it needs to be at least 1 diameter or 1.5 diameters thick, so that the pin has enough interference to properly self-retain itself in the assembly. And when that is retained on the outside and the inner part is supposed to rotate freely, it needs to be sized so that it always has clearance with the pin. And because of the nature of spring pins, they are larger than the hole when they're pre-installed, and once installed and they exit out the hole, they become slightly sized, though they will recover a portion of their original diameter. And that is something that we need to account for in the midsection of that hinge, so that it doesn't bind up, it doesn't introduce unwanted friction in there. So we do have some internal charts that help us calculate what the difference or what the hole size difference for the outside and inside parts should be in order to achieve that objective.
Okay, a follow-up question to the low temperature material question. So do you have test results for coil pins and slotted pins for temperatures as low as -40 Celsius?
No, we do not. We would make our recommendations based upon research of those materials' properties. And those are widely available. So, for example, if you have a cryo application where there isn't heavy cyclical loading, et cetera, then an austenitic stainless steel pin, as we had previously presented in the presentation, might be a really good choice for you. And then conversely, we can also manufacture parts that are specials out of Inconel. Inconel can be heat treated in 2 different ways. We can either heat treat it for use in a cryo environment, or we can heat treat it for maximum strength at elevated temperature. So to that end, again, we would base that upon individual case studies for your application and look at the material and study its properties at the temperature you desire to determine whether or not we can, number one, form it properly, so that it's manufacturable and cost effective. And then secondarily, that once we produce the part, it survives in the environment in which you need it to.
And Mike, I think this is also a great opportunity if the customer is really has this low temperature environment to engage us, provide us with a lot of the technical details of their application. And we could, freeze the pins to that certain temperature. And thanks to our in-house testing equipment for shear strength of the pin, we can actually test the pins and see how they would behave in that specific application.
Okay, great. Well, thank you, everybody. So for any questions that we didn't get to today, we'll provide the answers via email. And as stated earlier, we will make this recording available in the resources section on SPIROL.com, as well as on our YouTube page. Thank you so much for your participation. Thank you, Mike and Adolf, and have a great day.
Thank you all.
Thank you, everyone.